A huge thanks to my Patreon supporters for making this episode possible. Good morning, fellow mathematicians! Welcome back to another video. For the longest time now, since the start of the channel basically, people wanted me to do more competitive mathematics problems, and I thought, yeah, why the hell not? It's going to get me some new viewers, I suppose. Why not? We are going to dive right in. The first one is going to be an AIME 1 2015 problem. Problem number 3, and it's a number theory problem basically. What's the smallest prime p with 16p plus 1 being the cube of a positive integer? Meaning we can rewrite this at first as 16p plus 1 is equal to some, I don't know, r to the third power. Really doesn't quite matter what you call this thing. R is out of the positive integers, so n. Now we just need to check two cases at first. So whenever I present a problem like this, I'm going to show you how I solved it the first time around. It's not like optimized in any way probably. It's just how I solved it, and I don't know, that's mostly the best kind of solving a problem, how you did it on your own. So at first there are two cases for prime numbers, odd or even primes. The case with the even primes is really easy to check, okay? So the only even prime is 2. So what happens if p is equal to 2? Well, then we have 16 times 2 is 32 plus 1 is nothing but 33 being equal to some r cubed. Well, 33 is not a perfect cube. It's not. There's not a perfect cube you could find that gives you 33. It's just not something that happens. Alright, so with that case out of the way, we know that, well, p must be odd. So that's the first thing I did. Then, well, how can we proceed from this point onwards? Well, the cool thing is, there's something called the geometric progression. If you take a look at the geometric progression, this is just of the form k is bounded between 1 and n in some way, x to the kth power, and this is equal to, well, x to the n plus 1 power in this case, minus 1 over x minus 1. You might have seen this before. If you let n go to infinity, then this is just a geometric series. Meaning overall, if we choose n to be equal to 2, then that means that we have x to the third power minus 1 being equal to, if we multiply both sides by x minus 1, we don't want it to be equal to 0 for now, we don't know what the roots are going to be of this polynomial, then we are going to end up with an expression for x to the third power minus 1 in some way. How can we get x to the third power minus 1? Well, in our case it's r, and well, why not just subtract 1 on both sides, leaving us with, in the first step, r to the third power minus 1 being equal to 16p. Well, now we exactly have a geometric progression here, meaning overall 16p is thus nothing but, okay, on the one hand we are going to have r minus 1 as a factor in some way, so we are just going to factor a third degree polynomial pretty easily using this, and then what are we going to have as the other factor? It's just the sum that runs from 1 to, well, n in our case has been 2, so this is nothing but r squared plus r plus 1, and here it's as easy as it is. Now we can go through a few more cases overall. So at first we could divide both sides by 16, so why not do that? Meaning overall p, our prime that we are looking for, the smallest prime overall, is nothing but r minus 1 over 16 times r squared plus r plus 1. Proceeding from this point, how could you do that? Well, we could check for the parity, for example. Parity means, are we going to get an odd or an even number if we plug some integer into here, some positive integer? So let us check at first what happens if, for example, r were, I don't know, even, for example. So first case, case 1, r even, and that's equivalent to saying that our r is nothing but 2 times n, where n is element of the positive integers in this case, just because we wanted r to be a positive integer. Then this means that, let us just go through the kind of parity argumentation here. We are going to get something, okay, an even number minus 1, for example 2 minus 1 is going to give us an odd number because this is 1. So we are going to have odd over even in some way, Okay, then our P is odd over even times, okay, even number times even number. 2 times 2 is 4, so this is even. So this gives us even plus even. This is 2 plus 2, for example, is also even. Plus 1 is going to give us an odd number. So this is odd over even times odd. An odd number times an odd number, 5 times 5 is 25. It's going to give us an odd number. So the parity of this thing is odd over even overall. But odd over even is never going to be in the natural numbers, for example, the positive integers. I have proven this before. I believe in my How Do Mathematicians Prove Things. Link will be down there at the top of the description probably. Just as an easy example, let's take 3 over 2. It's 1.5. It just doesn't work because this thing is an even number plus 1 over even gives us 2 over 2 plus 1/2 in this case. Really doesn't work out. Okay, this is not element of n. Meaning overall, our R cannot be even in this case. Meaning the only thing that could happen is that our R is odd. Case number 2. R is odd. And that's equivalent to saying that R is of the form 2n plus 1 or 2n minus 1, really doesn't matter. Okay, it's the same thing, where n is element of n. If you do 2n minus 1, you need to place some more restrictions on your n that you are going to have here, because positive integers implies it's without 0. Okay, just and without -1 in this case. Okay, just as a little side note. So if R is odd, what is the parity of this thing? Let us go through this at first, just to verify if everything works out. P must also be odd, then, okay, it needs to be an odd number. So P is thus in parity. R minus 1 is 2n plus 1 minus 1 is going to give us overall an even number over an even number times, well, odd times odd is going to be odd. We had this before, odd plus odd, 5 plus 5 is even. Even plus 1 is going to be odd in some way. So we are going to have even over even times odd. Even times odd, 2 times 5 is going to be even yet again. So this is even over even, and this does work out. 4 over 2 is going to be, well, 2. So this works out, could be element of natural numbers. There's no contradiction here, it could. So now let us write out what we can gather for our P here by replacing R in some way with this 2n plus 1 expression. And I'm just going to do this for the first part because, well, it's just way easier then. Then our P is equal to, well, 2n plus 1 minus 1 over 16. Okay, plus 1 minus 1 is going to just cancel out to 0. Okay, and then we have 2n over 16. Well, it has a common factor of 2 on the numerator and denominator. This is just going to give us n over 8 overall. I hope you could follow everything I said here. Then we are going to leave r squared how it is and all the other r's here. So r squared plus r plus 1. Now we just need to plug in some n's with n at our hands. We also have the definition for r or value, and then we are going to see if we can find a prime number. What happens, for example, if we choose n to be less than 8, for example? What would happen? Well, then we would have, for example, for n being equal to 1, let us just go with n being equal to 1. Then it happens that r is equal to 3 in our case, and this means that p is thus, okay, this is 1/8 times, and then we just have some other factor here. So this gives us 3 squared plus 3 is going to be 12 plus 1 is going to be 13. 13 over 8 is not element of n. And this is going to happen if n is any less than 8. What were to happen, so with each and every case where n is not or is less than 8 in some way, we are going to get a fraction out just because of our n being less than what we have down here. It just is what it is. Okay, it's just going to happen. Then what happens if our n is exactly equal to 8? If n is equal to 8, then p is obviously, okay, 8 over 8 is going to cancel out, it's going to be 1. If n is equal to 8, then we are going to get 17 for our r. So this means this is 17 squared plus 17 plus 1. This is going to give us 17 times 17 is 289 plus 17 plus 1. This is 290. 290 plus 17 is going to give us 307. Now we need to check if it's a prime number, and if it's a prime number then it's the smallest one we could actually have for this problem, and then we are basically done. For this I'm going to just make use of the square root test, meaning we are going to take the floor of the square root of 307 and then we see what the biggest factor basically is that we can multiply something by, such that we could compose 307 out of prime numbers basically. So square root of 307 is so 17 times 17 is 289, so this is probably the closest we could get to there, so that's probably 17.3, I don't know what it is, but if we take the floor of this thing, it's just going to be 17. Now we just need to check all the prime numbers up until 17 if they divide our 307, and then we're done. So 2 obviously doesn't divide 307 because it's an odd number. 3 does also not divide 307 because 3 divides 306, so it doesn't work out. For 5, no, it doesn't work out because, well, we don't have a 0 or 5 at the end. What is this for 7? 7 doesn't work out because 350 minus 42 is going to give us 308, so this doesn't work out. For the number 7, what about the number 11? 11 doesn't work out because the alternating digit sum is 3 minus 0 plus 7 is going to be 10, it's not equal to 0. Then we have 13. That's also something that could work out. This is going to give us 260, and then 5 times this is going to give us 310. No, doesn't work out. And this has been the last prime number before 17, and 17 doesn't divide this thing because, well, we have plus 1 here. Okay, if we would have another 17 here, then it would be divisible by 17, but it doesn't, meaning 307, smallest prime. I hope you could follow everything I did here. So I just went in my head through all the prime factors that could be less or equal to 17, and none of those divided 307, and this is why it's a prime number, and it's also the smallest one here. I thank you guys for watching. If you enjoyed this video, please like, subscribe, recommend, channel like. If you want to support channel a bit more, by the teachers I create, blah blah blah. If you want to see more math competition problems, then please tell me so. Hello kitty kitties, nice to have you here. I would love to draw some new viewers in, and I believe that posting some math competition problems is going to do the trick over time. So send me some math competition problems if you have some at your hands, and up until the next video I'm wishing you guys a flammy day. Ciao! Jetzt nagen die. Toll.